Kristen.
Okay, thanks, Carl and Kartik. Hi, everyone. I'm Ruohan Gao. And today, I'm very excited to present our work ImToFlow, motion hallucination from static images for action recognition. So this is joint work with Buch and my advisor, Kristen Grauman from UT Austin. So recognition of human actions in videos is a challenging task. Given a single frame, we can exploit the objects in the image to recognize action. The body pose and the scene context can also provide useful information for action recognition. So these are all appearance cues, except for these cues that exist in a static frame. Observing the video on the right, it's easy to recognize that the man is doing push-ups. Motion is therefore another important cue that is very useful for action recognition. There are many video-level action recognition methods exploit both appearance and motion. In prior work, motion is usually represented by various forms such as optical flow, trajectory, or other localized spatial-temporal descriptors. So optical flow is the most direct motion information used for action recognition and still commonly used. However, unlike videos, motion cues are missing static images. Given these static images, we can still recognize the action that are taking place in them. For example, among these static images, we can easily recognize a man doing push-ups and a woman doing high jumps, etc. Unlike video-level action recognition, without motion, static image action recognition methods exploit various high-level cues such as body pose, objects, and scene context. However, is motion really absent in static images? Over many years of observations, we humans accumulate visual experience about how things move in the world, just like we are watching a lot of unlabeled videos. Given a single static image, not only can we interpret the instantaneous semantic content, but also we can anticipate what is going to happen next based on the human poses and object configurations presented in the image. For example, we can expect the person's back in this static image is either to move up or down, and this may also help the recognition of the action in the static image. Actually, a neuroscience study reports similar results. Neuroscientists examined the activation in humans' medial superior temporal cortex when showing people static images with implied motion. The MTMST cortex is one of the main brain regions engaged in the perceptual analysis of visual motion. So here are their experimental results of the anatomic images of human brain. They use concentric rings as a visual stimuli. When they show people the stationary rings, this part of the region is not activated. And then when they show people the moving rings, the rings moves with 7 degrees per second, this part of the brain is strongly activated. Then they did another group of experiments and show people static images without implied motion, and MTMST cortex is not activated. And then when they show people static images with implied motion, with strong motion likelihood, this part of the region is strongly activated again. So this suggests that the brain regions involved in the visual analysis of motion are also engaged in processing implied dynamic information from static images. Our idea in this paper is inspired by these observations. Our idea is to learn from the massive unlabeled videos and accumulate the visual motion prior by watching videos. Then, given only a static image, we can use our ImToFlow network to transfer the learned motion from videos to static images to hallucinate their motion. Finally, by combining the appearance from the original static image and the motion from the inferred flow image, we can leverage the predicted motion to help recognition. We formulate the problem as an image-to-image translation problem. Firstly, we decouple the optical flow UV vector into 3 separate components, each indicating one important factor of motion: the vertical direction, the horizontal direction, and the motion magnitude. This makes the high-dimensional motion prediction problem more factored. Prior methods have other ways to encode optic flow, and we find out that our method of detangling flow direction and the strings presents an either learning task. Encoding motion as a 3-channel image also makes its usage efficient, convenient, and suitable for our image-to-image translation framework. So let X be the domain of static image containing an action, and let Y consist of the corresponding flow image. Our goal is to narrow mapping G from X to Y to infer flow from an individual image. We devised a convolutional neural network called ImToFlow to obtain the mapping. Our ImToFlow network is an encoder-decoder network. The network minimizes a combination of 2 losses, a pixel error loss and a motion content loss. The motion content loss network is fine-tuned for action classification. Using flow images as input, it thus encodes realistic motion, so it's useful for action recognition. The pixel loss is the L2 loss between the predicted flow image and the ground truth flow image. It encourages the pixels of the output flow GX to exactly match the pixels of the target flow Y. The motion content loss is the L2 loss on the activation maps extracted from the motion content loss network phi for the predicted flow and the ground truth flow images. It encourages the output to have similar high-level motion representations as the ground truth flow images. The image flow network that learns to predict motion based on a single snapshot. Let's now see some results. We first directly evaluate on flow prediction. We evaluate on test set from UCF101 dataset, HMDB51, and the Wiseman datasets, and the table shows results from the UCF101 dataset. We compare rhythm matrix adopted from prior work, the endpoint error, direction similarity, and orientation similarity. And we evaluate over all pixels in the whole image, and also the masks on candy edges. So candy edges is an approximation to measure the error of moving pixels in simple things. And we also evaluate masks on foreground regions, and the foreground regions usually correspond to the moving objects. So we can see that across all metrics, our method consisting outperforms all our baseline methods, including the only two existing prior methods on static image flow prediction. It demonstrates the effectiveness of our motion encoding scheme and the motion prediction network. So here are some qualitative results. Given a static image, we infer flow and visualize the flow vectors of the top motion strength. The color will visualize the direction of the flow vector. For example, red means the rightward direction. We can see that our model makes reasonable predictions across various parts of the image, and the predictions are pretty fine-grained. And here more results will be shown as a video. But note that the prediction is per image based. So we perform no temporal smoothing between frames estimates, and the last column shows the ground truth flow. We can see that the prediction results of the baseline method is coarse compared to our method. And in this baby crawling example, our model can predict motion at various body parts of the baby. Here are more results of a woman doing pull-ups and a man doing push-ups. And apart from human motion, our model can also predict scene motions, such as the falling waves in the ocean. Our motion prediction model is far from perfect. Let's see some failure cases. Our model can fail, especially when the background is too diverse, or the motion presented in the static image is too subtle. Under these circumstances, it's hard to capture the motion based on only a single snapshot. The signals are either too noisy or too weak. So with the ability to anticipate flow as an additional benefit of our image flow framework, we can use it to infer the motion potential of the level image, that is the strength of movement and activity that is poised to happen. We define the motion potential score as the average magnitude of predicted flow normalized by the size of the foreground region. So here are some images that are identified to have high motion potential score by our framework. We can see that these images capture critical moments of intense motion for some action, such as high jumping and surfing. And here are some images that are identified to have low motion potential score. It makes sense because actions such as playing pool has very subtle motion, and it is hard to notice in a static snapshot. So we've just seen the results on flow prediction. Now let's see the impact of in-flow on action recognition in static images. To perform static image action recognition, we train an appearance train based on the original static images and perform prediction based on appearance. And then we use our M2Flow network to predict the corresponding flow images for each static image. And we train a motion stream and make predictions based on inferred motion. Finally, we perform action recognition by combining the prediction from both the appearance stream and the inferred motion stream. So how exactly does inferred motion help recognition? The image shows a woman applying eye makeup. However, brushing teeth, applying eye makeup, and applying lipstick are all visually similar. So showing the hand movements of women guides the classifier to make the correct prediction. Here are more examples of how the inferred motion can be used to correct the original wrong predictions. So overall, motion helps to provide a salient signal for action that can be difficult to learn directly from the images alone. And the motion implied for people and objects in the static images can help to better distinguish subtle differences among such actions. Because our M2Flow network leverages a large amount of videos to build the motion prior, it can also help to regularize the activity learning process. We evaluate static image action recognition on 6 datasets. Firstly, we construct 3 static image datasets from existing video datasets. So to construct these datasets, we only extract the center frame in each video. Since they are originally from video, these datasets allow us to compute the actual flow. We also evaluate on 3 static image action benchmarks: Vino, Stanford 10, a subset of Stanford 40, and Pascal 2012 actions. It's important to notice that these datasets contain novel actions that our im2flow network is not trained on. We thus also test the model's capability to generalize to novel domain or even novel action categories. Let's see the results. This is the result of the baseline method. The predicted cost motion works poorly for recognition. And this is the result of our method. The inferred motion from our im2flow framework performs much better. Here is the performance using ground truth motion. Our motion stream performs even closely to ground truth motion in some cases. And this is the performance of the appearance stream. It is trained on the original reliable static images and performs better in terms of the single stream performance. But still, by combining it with the inferred motion, we can improve the recognition accuracy by 1 to 6% relatively across all 6 datasets. Note the test images are from different domains from that are used to train our im2flow network. So our approach generalizes well due to the motion prior transfer from unlabeled videos to static images. And on the window dataset, we performed additional experiments using various base architectures. And by inferring motion, we also performed a series of state-of-the-art methods. Except for human motion, motion is also indicative in many dynamic natural scenes, such as waterfall, falling trees, and rushing river. But given a static image of a dynamic scene, hallucinating motion from the scene may also help recognition. So if we evaluate on the YUP++ dynamic scene dataset, by inferring scene motion, the recognition accuracy improves from 74% to 78%. So it's improved by a large margin. So in conclusion, we have proposed an approach to hallucinate the motion implied by a single snapshot, and we've designed an im2flow network for dense flow prediction. And we have demonstrated that the inferred motion can help to enhance recognition of actions and dynamic scenes. Welcome to visit us in the post section, and thanks for your attention.
So we have time for a few questions. So if you have questions, please come up to the microphones, down the aisles. Whilst you're waiting, so I was just wondering if the motion was slightly more long-term. So optical flow is great for relatively short-term motions, but how would you be able to consider?
Right. That's a great question. So yeah, currently I will only consider optic flow, which is only computed by 2 adjacent frames, but it definitely will be helpful to analyze some long-term motion representations, and we learn from those long-term motion representations to aggregate them to select dynamic images, and we can also to infer a dynamic image from a select static image to help recognition. That will be interesting to explore. Yeah.
All right. Are there any more questions? Okay. If not, let's thank the speaker again.
Okay, so next up, we have Finding It, Weakly-Supervised Reference-Aware Visual Grounding in Instructional Videos, and the talk will be given by Shyamal Buch. And if there's any spotlight presenters, please come to the front of the room where you can sit.
What is that? I'm just going to hit this. Okay, cool.
Awesome. Let's get started. Hi, everyone. My name is Shyamal Buch, and today I'm really excited to be sharing some of our work on Finding It, Weakly-Supervised Reference-Aware Visual Grounding in Instructional Videos. This is joint work with my collaborators at Stanford, as well as my advisors. So when we want to learn something new, we go onto YouTube and watch instructional videos, like how to make a Caesar salad. But crucially, when the instructor says something like, now take the green mixture, we know that they're referring to this specific bowl in the scene. And this is called visual grounding. It's the task where we map a free-form text entity to a bounding box proposal somewhere in the scene. Now, these phrases don't necessarily have to be just nouns. They can also be pronouns, and even omitted entirely and left as implicit objects. And these later two cases make it really challenging to determine without any context how we're supposed to resolve what it is. And so in order to find it, we really need to take this context into account. Now that we know that it refers back to salad greens, we can disambiguously map it to that particular bounding box. So our first objective is to jointly resolve contextual references for visual grounding. Now, we can think of this sort of structure as kind of like a graph overall structure with nodes and edges. And in order to do fully supervised learning, we have to annotate these full graphs over videos, and this can get very costly. So our second objective is to try to find a way to learn how to infer these graphs without any grounding or reference annotations during training. So overall, if we combine the two objectives, our goal is weakly supervised, reference-aware visual grounding. Before we delve into the technical details, a brief aside to describe why we think it's so important. So, as I said, we already have a ton of instructional videos on the web, and improvements in automatic speech recognition mean that we are getting more and more time-aligned transcriptions. But we still don't have a clear way to use these to train or teach interactive autonomous agents. And so we think that moving from a step-by-step decomposition to a more grounded causal dependency graph structure is a key towards moving towards these types of applications. All right, now let's delve into the technical details. We can think of this as a sort of graph where the input nodes are actions and entities, which we can obtain through syntax parsing, And in the visual space, the nodes are bounding box proposals, which we can get through a region proposal network. And our goal is to infer the edges, the reference edges, which map entities to actions, and the grounding edges, which map entities to boxes. We propose a joint framework that has both reference resolution and visual grounding components, and we tightly couple them. Together, they work synchronously to resolve both the references as well as the grounding edges in the overall graph. Let's take a look at the grounding model in a little bit more detail. We perform grounding by comparing the embeddings from the entities and the bounding boxes. From the entities, we have an entity embedding, which can be obtained from a recurrent network. And the visual embeddings are through a convolutional neural network. And we rank the similarity between these entities and boxes to find the best match, and that becomes the grounding edge. Now, how do we learn how to perform this without object level, bounding box level supervision? Well, what we do have is alignment between the different captions and the different images. And these image caption pairs allow us to leverage multiple instance learning, where we can use the event alignment for weak supervision. As an example, if we, during training, ground salad greens to somewhere in the bag of proposals that are associated with the burger, we can consider that as a negative. Whereas if it grounds somewhere in the same bag, that would be a positive. And this is kind of the method that we can apply using standalone image techniques in prior work. Now, the key challenge is that in videos, these events are not independent, and that breaks fundamental independence assumptions. In this case, it's unclear if it was grounded to its referential context. Is that considered correct or incorrect? And so we propose a new reference-aware multiple instance learning framework that has two key components. The first is that we propose to perform grounding over not just the entity, but the entity and its subgraph. And this is really important because the reference-aware entity embedding, which is sort of defined recursively, means that it is unique for a given instance of the object at a particular time step. And this allows us to make a conditional independence assumption. So now, grounding it to its contextual bag would be considered a negative, and distinct from grounding it to its own bag, which would be considered positive. Now, the second component to this is when we focus on the two sets of negative bags we have here. Clearly, the burger bag is less relevant to the grounding than its referred context. And so our second aspect to reference-aware multiple instance learning is to use the reference relationship strength in the optimization loss. In this way, we disambiguate these two bags by giving sort of partial credit if it is grounded to its somewhere in its context. Cool. So now let's take a look at the reference resolution model. To recap, the goal of reference resolution is to map entities back to their source actions. We can think of instructions as sort of functions with outputs as new entities, and we want to try to recover these. So let's say we have two events here. What we do first is we encode them using a hierarchical recurrent neural network. And this gives us these source action embeddings. During our decoding step, we encode a flattened version of the instructions. And at each entity time step, we perform a content-based attention mechanism to perform a pointing operation linking an entity such as it back to its source action. And note that some entities don't actually have source actions, so we consider those to be background and map those accordingly. Note that our reference resolution architecture is also grounding aware in the same way that our visual grounding model is reference aware. And the way we do that is when we fix the grounding model, we pass in the grounded convolutional network features in addition to the glove word embeddings for each of the entities. So overall, our joint training approach is done through alternating optimization, where we freeze one and train the other. For the reference resolution, this is done through hard EM, and for the visual grounding, it's through the reference-aware multiple instance learning. For our data set, we leverage two different data sets, uCook2 and RoboWatch. And these data sets have cooking recipes as well as general how-to instructions. And they provide temporally aligned instruction step captions. Since this is a sort of new task for instructional video understanding, we provide test set annotations for the graph components. That is the bounding box and parsing edges, or nodes, and the reference and grounding edges. Now let's take a look at our results. We'll start with the visual grounding model. Cool. So as I mentioned before, with visual grounding, we have three different types of entity phrases we could have: nouns, pronouns, and implicits. So here's an example of a noun that's a sort of output of previous time step, pizza. And a standalone method is unable to localize it well at this oblique angle and close-up. However, if we include the context, our reference-aware approach is able to provide a stronger localization. With pronouns, we observe a similar trend as well. The standalone method is unable to tell where in the clutter scene we're talking about for it. But if we have the appropriate context, our reference-aware approach is able to localize it more precisely. And finally, we observe improvements over implicit entities as well. Here, the implicit is referring to on top of the onion rings. That's sort of omitted. The standalone method doesn't know this. But our reference-aware method is able to link this back to a prior time step and provide a better grounding. We observe this quantitatively as well. Here you can see the top one accuracy at IOU greater than 0.5. We report the proposal upper bound and random as a sort of upper and lower bound on the task performance. We observe that the standalone image approach is able to do reasonably well, but with our reference-aware method, we're able to improve substantially. We also observe that our improvement is consistent over different levels of graph complexities. We also analyze our errors. Since our references are inferred, if we infer incorrect references, like in this case, where flower is a background action, has a background action, then we observe that the grounding becomes less precise. And this is the case in both of these examples. We also benchmark the generalizability of our approach. So here we train on uCook2, and we examine in-domain generalization to RoboWatch Cook. In this case, a new dish of beef jerky, as well as out-of-domain tasks, such as how to clean a coffee machine. And then finally, we can see that this generalizability holds even quantitatively as well. With cooking, the performance is roughly comparable, and with the out-of-domain, the generalization trend holds. All right, cool. So we've looked at the visual grounding model. Now time for the reference resolution. We can observe that our overall method, our architecture improves overall performance, and the grounding improves that slightly further. And now finally, we combine the whole thing together. Here we have an input instructional video, and this is our output visually grounded action graph. If we take a closer look, we can see that the model is able to provide grounding and reference edges for the different, if you will, subtasks in the overall cooking task. So here the task was how to make spaghetti and meatballs. And we can see this decomposition hold over the full video. After making the meatballs, we cook them, set them aside, prepare the sauce. And then we combine all the ingredients together to make our final dish. This is really exciting because this type of graph is very easily convertible towards a grounded dependency graph structure. And it's a step in the direction towards autonomous interactive agents. I'd like to thank our sponsors. And we didn't have enough time to cover a lot of our prior work. But if you guys stop by the poster, we can discuss that as well. Thank you guys so much.
Okay, thank you for the great talk. We have time for one or two questions. It's hard to see up here. Okay, well, one question I had for you was, how often is there one-to-many mapping where it's harder to resolve where it should go?
Yeah, that's a really great question. So the question was, how often is there a one-to-many mapping on when it may be mapping to multiple things? So in this case, the way that we define the mapping, if it refers to like a collection of things, let's say it was a collection of toppings on pizza, the grounding in the current formulation is to the bounding box that encompasses all of them. But certainly, I think that's a really exciting area for future work. I will say one other thing that we didn't get a chance to discuss very much in detail here is that we actually, for each event, we sample multiple frames in the temporal span. And it's very possible that, and often the case, that the same entity is present in multiple of those frames, in which case the model is able to ground sort of across the multiple frames. It really depends on how you post-process the similarity scores. If you apply softmax, you'll get a unique solution. If it's a sigmoid and some top 5, then you can get multiple.
Cool. Thanks so much.
Awesome. Thanks, guys.
So the next talk will be on actor. Sorry? This one. So the next talk will be on actor and action video segmentation from a sentence, and it will be given by Kirill Gavrilyuk.
Hello everyone, I'm Kirill Gavrilyuk. I will present actor and action video segmentation from a sentence. It's a joint work with Amir Ghodrati, Zhenyang and Snoek. So our goal given an input video and set of queries, for example, woman in purple dress running with a dog, and a gray dog running on a leash during dog show, we want to segment these instances in the videos and have this segmentation as output. To compare with the conventional action localization setting, yeah, thank you. In conventional action localization setting, we have a predefined set of actions. We want to localize objects with the bounding boxes, and most of the time we concentrated only on a human actor. Differently, in our setting, we use specification by sentence, so we have open vocabulary textual description. We prefer to do segmentation instead of bounding box localization. And we also work with any actor types, not only humans. So there are works that perform a task from a sentence. For example, there was a work in ECCV 2016 doing image segmentation from a sentence. So instead of segmenting objects according to class label, for example, like horses, they concentrated on one particular instance of a horse according to a textual description. Another work is from CVPR 2017. It's a tracking from a sentence. So instead of specification of a target in the first frame with a bounding box, they specify a target with a sentence description. There are also work concentrated on actor action video segmentation. So they use a predefined set of classes. So in 2015, Xu et al. Proposed dataset with 4,000 videos with seven actors performing 8 different actions. And actors can be very different, for example, adult, baby, or dog, cats, and also non-living objects such as balls, cars. In ICCV 2017, Collagate and al. Proposed method to perform actor and action detection and segmentation using single RGB and flow frames as input to the model. So to perform our task, we extended two existing datasets, actor and action dataset that I presented previously on the slide, and GMSDB dataset. We extended with sentence descriptions for the whole videos. And yeah, we have more than 7,500 descriptions available for these datasets. Going to our model. So as input to our model, we have sequences of frames, for example, RGB frames, and we also have a query, for example, a man in dark suit standing in the back. So we encode a video sequence with an i3D model. We perform on the last layer averaging pooling to get representation for a frame in the middle of video sequence. And we use i3D pre-trained on kinetics and ImageNet datasets. We encode each word in the sentence with a word-to-vec embedding pre-trained on Google News dataset. We use a convolutional neural network to encode the whole sentence and to get a vector representation of textual description. We use deconvolutional layers to upsample video presentation to original resolution. And from sentence representation, we create dynamic filters. Basically, it's convolutional filters, but instead of in traditional convolutional neural networks, they are not static. They are dynamically generated from sentence descriptions. So for different queries, we will have different filters. We convolve these filters with the video presentations at different resolution levels, and we output this responses map for all resolutions that we want. So we use these 3 resolutions during training, and during testing we use only highest resolution response map. So we perform a bunch of ablation studies. First, we study the question if video is beneficial for our model. So we studied our model performance with the different number of frames, for example, with 1 frame and also with 16 frames, and we saw increase in performance when we use more and more frames. We also studied that multiple resolutions are essential to better training of our model. And also we studied how to encode texture representations, and surprisingly we found that simple 1D convolutional neural network is outperforming LSTM and also bidirectional LSTM on this task. We also compared with 2 image-based approaches that was presented in a related work. It's one for image segmentation from a sentence, another one is tracking from a sentence. So both models were pre-trained on a referred dataset, which has referring expressions for only images. So as input, they have RGB frames, independent RGB frames. So we studied their performance out of the box, so we didn't fine-tune them and just applied for video sequences. We also fine-tuned them, and we saw a large increase in performance. The main explanation is that in images they don't have understanding of actions, while with fine-tuning we make them understand actions better. In our model, we further increase results with RGB only as input, and with floor our results even more better. Yeah. So going to some qualitative results, we studied simple cases. For example, when there is one large object almost in the middle of the frame. For example, on the left there is a kid rolling over, and on the right it's a brown dog rolling on the ground. We have very reasonable, nice segmentation results in this setting. Also, we studied more harder cases when query descriptions differ only with the action. There is the same type of actor, but different types of actions. And we can still separate them quite well. But of course, we have failure cases. One of the interesting failure cases that we cannot separate fine-grained categories, for example, man and woman. So basically, we have almost the same queries as input, differing only that we want to concentrate on man, and in other query, we want to concentrate on woman. Basically, we output that it's all woman. We compared with the image-based approaches also qualitatively. So there are several main interesting cases. For example, we are better with small objects. For example, on the first row, you can see cat climbing a wall. While image-based approaches cannot segment the cat, we can do it because we have access to the video, so we can see cat more easily. The second row shows that image-based approaches concentrated on some distinctive part of the car, like wheels, but cannot segment the whole car, while we can do as well. We also compared with the traditional semantic segmentation. So instead of open vocabulary queries as input, we use actor and action pairs from original actor and action dataset. So for example, we use ball flying as input to our model. So we compared to state-of-the-art methods on actor and action dataset for setting when we want to perform a segmentation only for actors like ball and adults, so we don't care about actions. In this setting, we perform on par with the state-of-the-art method, but when we want to perform segmentation for actions, we're much better than state-of-the-art. And combining all together, results is also better. So in conclusion, I want to say that sentence awareness is beneficial to specify actor and action instances, and also video awareness is beneficial for more accurate segmentation. So for more results and discussion, see you at the poster. So thank you.
thank you for your talk. I can see there's one person.
Trying to, oh,
Yeah.
okay. So I have a question regarding the dynamic filter you mentioned. How does it perform on different sentences, and is there any idea behind the different spatial resolution that they apply?
Sorry, I didn't hear.
Can you please repeat
Yeah,
that? It's
sure.
not very clear.
I asked how does the dynamic filter perform on different sentences, and what's the idea behind the different spatial resolutions that you combine with the appearance? The main question is, what's the dynamic filter applied on the sentence?
So dynamic filters is basically it's convolutions generated on the fly from a sentence. So if sentence contains like different objects, for example, dog, so dynamic filter will try to find dog features in the video representation. If it contains, I don't know, adult or human, so it will concentrate only on human feature maps from video presentation. Okay. Is it answers the question?
Yeah, and the second question was, what's the idea behind the different spatial resolutions on? Because I saw you use 3 spatial resolutions.
Yeah.
Why is that?
It actually helps to better propagate gradients in our model, and to concentrate also on small objects and large objects altogether.
Okay, thank you.
So are there any other questions? Please wave. It's a little difficult to see from here. So. Okay, so if not, let's thank the speaker again.
Yeah, thank you.
So we're missing three to four spotlight speakers. So please come up to the front of the room and sit. If you don't come up, the chairs will have to present your spotlight, and you don't want that. So we have this last talk in the session will be egocentric activity recognition on a budget, and will be given by Rafael Postis.
Okay, thank you. Good afternoon, everyone. Today I'm going to present the work we've been doing at the University of Sydney in the last year. And this was a joint work between me and my colleagues, Sheila Cáceres and Fábio Ramos. Before we start, I can actually give you some statistics. It's projected that the combined geriatric and senior population can reach 2.1 billion by 2050. And what that actually means and how could AI help? We know that this aging population puts a lot of pressure on carers and nursing services, and those professionals, they actually rely on some sort of activity tracking to perform their duty. And this activity tracking is mainly relies on dedicated human assistants. That's where egocentric activity recognition comes into play. This is a method to classify subjects' activities of daily living, and it's based on data collected from smart glasses. The data from those smart glasses is usually user vision and head motion. And we've seen already that detecting daily activities can actually improve people's lives. And how that actually happens in our case. We could provide automated reminders or warnings through the EAR system to potentially avoid any dangerous situation that these people with some sort of cognitive impairments might have. However, when trying to solve this problem, we got some constraints. We know that smart glasses, they have not only small batteries, but they also have very limited processing power. And if we look at the recent deep learning development, and we see that most methods, they are highly accurate, but they are also very resource intensive. So we end up dealing with an optimization dilemma, which is, should we choose higher accuracy or extended battery life? And if we go further and look at the related work, we can see that most methods, they rely on some sort of multimodal or multi-stream approach, where we have different streams of data. In the case of egocentric activity recognition, we have egocentric videos and sensor data. And on the first, we need to extract features either manually or automatically. And on the second, we need to use some sort of temporal models because we wanted to capture the correlation between the data points. Then we get these features and we merge them into a fusion layer. first fusion layer, then we merge again into a final fusion layer that gives us the class predictions. When trying this kind of model, we've noticed that it doesn't work for our problem because it has very high energy requirements. Not only we have an increased model complexity, but we also use expensive sensors such as the camera continuously, and we know that for any mobile device, this is not feasible. So how could we actually reach energy efficiency through feature selection? In here we have two activities where you can see that from the camera point of view, we have features that we can extract, we have objects that we can detect. But if you look below at the sensors, they almost have no motion. They are more stationary. So in this case, we could easily use a vision-based model to provide a prediction and not care about the motion itself. But on this other case in here, we see an activity with a lot of head motion, but not many objects to detect or not many features that we could use from a vision sensor. And if you see below the motion sensors, they have a very distinguishable pattern. So in this case, we would actually use a motion-based model to provide the prediction. In the end, then, we have a feature selection and energy consumption optimization. On one hand, we have vision predictors. They are more accurate, but they also demand more energy. And on the other hand, we have the motion predictors. We've seen that they offer a better trade-off on activities with distinguishable body movement patterns. And we've seen also that the pervasive use of EAR is conditional to methods that they are both accurate and energy efficient. So this raises our question that motivates our work. Could we actually learn a policy that not only trades off energy consumption and accuracy, but also exploit each predictor's performance? And in order to exploit that, we are looking into learning the user context. Our solution is a reinforcement learning approach where we have an environment that in our case is made of activities. These activities, they have some sort of continuous representation. We can gather data from accelerometer, gyroscopes, cameras, and we need to decide how we are going to represent our state. In our case, we represent our state through the sensor readings. And why is that? Because sensor readings are pretty cheap to collect. We can keep them on and it's not going to hurt the performance of the battery. And we need some sort of function approximation to do that. In our case, our policy is approximated by an LSTM network because we also want to keep the correlation between the data points. And our policy has two actions, which is we either choose a motion-based predictor or we choose a vision-based predictor. In the case that we choose a vision-based predictor, it means that we also need to turn on the camera. We keep the motion sensors on at all times for state estimation, and the energy efficiency, we save energy on that by avoiding forward operations on the network, on the model, but on the vision predictor, we save energy by not only turning off the camera, but also avoiding a specific vision model to run the feed-forward operation. And we give a reward for that. The reward is actually based on the accuracy and the energy expenditure of the chosen predictor. And in the end, what we are looking for in here, we are looking to maximize the long-term reward by choosing actions that best trades off energy consumption and accuracy. So in order to understand this a bit further, we need to understand what is the reward function in the reinforcement learning framework. This is actually what drives the gradient updates. This reward function will actually tell what to do in each state. And our policy has a very simple design. We take an action. It could be use a vision-based model or a motion-based model, and then we need to evaluate this action. Was that prediction correct? If the prediction is correct, we also need to understand if we had chosen a different action, what would be the prediction? And we give a reward that is based on this relationship. So let's look at some examples. If we use a motion action, we decide to use a motion-based model, we see that we got a right outcome in this case, but if we look at the vision model, it would also provide us with a right prediction. In this case, we give a reward of only 1. However, if we choose a motion model and both predictions are wrong, we give -1 because we want to perform a gradient descent and we are not optimizing, maximizing our reward. Now it gets interesting. If we choose vision, this is where we want to save the energy. So in our case, whenever we choose vision actions, we need to be careful with that, and we provide a hyperparameter lambda that actually increases or decreases the likelihood of taking such actions. In this example in here, we can see that if we choose a vision sensor for prediction, and that actually gives us a right outcome, And when we look at the possible motion sensor predicted and that would not be able to provide us the right outcome, that means that we are exploiting the strength of that model. In this case, we give 1 plus lambda. But if the opposite happens and our vision sensor is not able to provide a right prediction and we could have the right prediction with a motion sensor, we give -1 minus lambda. And in the case that we choose a vision sensor model, but both sensors would provide us with a right prediction, we only give lambda. This is because we want to keep the direction of the updates, but we want to reduce the magnitude. This is not an optimal action to the reinforcement learning framework, but we still have a right prediction. So it's not the best, but we are increasing the accuracy in this case. So if we look at the separate models that we use, we have a vision predictor that has as an input sequential images. We first extract the features through an inception V3 architecture. Then we feed those features into LSTM for sequence learning. This is a model known as long-term recurrent networks, and it works really well with sequence of images from the camera. The output of the model is the class prediction. And for the motion predictor that we use through accelerometer and gyroscope, we use a plain LSTM, that the input is 10 sequential readings from accelerometer and gyroscope, and the architecture is just 64 neurons a row through time. And we've seen already that this model is very strong for activities with very specific body movement patterns. The output is also the class prediction. We put everything together to an actor-critic method for policy search. And the main thing about this method is it uses multiple workers to update one single global policy. This parallel optimization actually helps to decorrelate gradient updates, which is a known problem in reinforcement learning. And we also use an advantage function instead of discounted rewards. This is a baseline method in reinforcement learning as well that also helps to decorrelate, to reduce the variance on gradient updates. More details on the optimization process can be seen on the paper or at our poster. For the experimental setup, we have 2 different data sets with 20 activities each. We have a benchmark data set that we call multimodal. This data set has around 180 minutes of data with 1 activity per video, and each video has 15 seconds. We find that this data set is not very realistic. Then we recorded our own data set that has 400 minutes of data with 6 to 5 continuous activities per video of 5 minutes. The sensor and camera, they were recorded at both 10 hertz and 10 frames per second. So let's see some results. In here, from left to right, we have an increase in sensor usage and also in accuracy. And we can see that on the extreme left, we have a very energy efficient model, which is a motion-only approach, with only 61.24% of accuracy, but at a cost of 150 million per hours. And as we go to the right, we have the state-of-the-art accuracy on this task, but also they are very energy intensive, as we discussed before. So what is our goal? We want to learn policy that can sit anywhere in this line, and we do that by changing the hyperparameter lambda of our framework. So if we take a look at that, we have this plot that we have the power consumption against the usage of devices for different values of lambda. So what happens when lambda equals to 0? We have a policy that is very conservative. We have 92% of motion usage and 8% of vision usage, but that small vision usage is already able to increase the accuracy by 3% when comparing to the motion-only approach, and that at a cost of 24 million pairs hours of energy. Let's increase lambda a little bit. We have lambda equals to 0.2. We found out that this is the soft spot of our policy because we have a balanced usage between vision and motion sensor with roughly 50% each and an accuracy of 81.33%. That already beats one of the state-of-the-art methods in the accuracy, but only at half of the energy cost. Let's go further. Lambda equals to 0.4. This actually learns a policy that is really greedy. We can see that the policy has 95% of usage in vision sensors and only 5% of motion. We are able to beat the state-of-the-art accuracy on that by roughly 0.9, and we use 30% less energy in this case. But that's not enough. We need to understand if the policy is actually learning the context that we wanted it to learn. In here, we sample the last softmax layer from the policy with lambda equals to 0.2. And we can see that on extreme left, for more stationary activities, we have vision actions taking over motion actions. And if we look at the extreme right, we see the opposite. Motion actions are taking over vision actions because those activities, they probably have very high motion movement. So in summary, we've shown that we can use reinforcement learning to learn policies with different energy profiles, and also that learning the user context is key if we want to leverage the synergy between motion and vision sensor. And one last remark, that whenever we are implementing things for mobile devices, energy consumption should always be a metric as long as we have accuracy as well. The data set that I've shown to you in here is available in the link in this slide, and I'm happy to take any questions now or at our poster in B1. Thank you.
Thank you so much.
Thank you.
Are there any questions in the audience? You can, oh, there you go, okay.
Hi, very nice work. What would you expect your framework to behave like when you have highly correlated modalities, like maybe not like vision and motion, but vision and vision?
Yeah, that's something that we foresee for future work. But since we are using LRCN that captures the correlation between the data, and the policy also have that, we expect to be able to capture that.
You still expect benefits, basically?
Sorry?
You still expect benefits from individual, respect to using individual...
Okay, individual features you mean?
Yeah.
Yeah, we could have benefits depending on which point of view we are looking for, because we are using Egocentric. So it depends from where the other video would actually capture the data. We could see benefits for that.
Okay, well, thank you.
Any other questions? Okay, let's thank the speaker again. Okay, so that concludes the oral session. Now we'll begin the spotlights. We're missing the first spotlight speaker, so please come up.
Good afternoon, everyone. This is Lin Chao from Tencent AI Lab. I here present our work named CNN in MRF for video object segmentation. We address the problem of a semi-supervised video object segmentation, where the ground truth mask of objects of interest are given in the first frame of the video. The problem is essentially a combination of segmentation and tracking, with difficulties from both problems, such as occlusions, object associations, and fast motions. The problem is usually formulated as MRF inference problem, but recently convolutional neural network-based methods achieve outstanding performances on challenging benchmarks. However, the CNN-based methods are mostly handling each frame individually, such as the well-known methods Oswald and mask track shown here. In this work, we combine CNN and MRF to solve the problem. Specifically, we model all the pixels in a video as an MRF, whereas the unary term and the temporal term are modeled similar to conventional MRF model, but the spatial term in our model is defined using a feed-forward CNN. Intuitively, given a mask configuration of a frame, we can define the spatial energy of the frame using the Euclidean distance between the mask and the ground truth mask of the frame. However, the ground truth mask is unavailable. fortunately, we can use a mask track style CNN to approximate the ground truth mask and compute the spatial energy as the distance between the mask and the ground truth mask proxy generated by the CNN. Notice that the inference in the resulting MRF model is very difficult due to the involved CNN term. We here decouple the CNN term from the other terms by introducing an auxiliary variable and minimize the objective function by alternating between solving the two subproblems, where the first subproblem is a large quadratic integer programming problem, which we approximate using ICM method for efficiency. And the second subproblem still has a very high order energy due to the CNN term. Luckily, we can approximate the solution using a feed-forward pass of the CNN used for the energy definition. We experimentally verified that the approximation can make the objective function of the subproblem non-increasing in most cases. Thus, the alternating between the two steps can converge into a solution of the overall inference problem. The resulting algorithm is very simple. It alternates between a temporal fusion step and a mask refinement CNN step. The CNN is actually defined for the spatial energy computation. We initialize the algorithm using the results from the OSFOS with linear motion tracking and obtain the unary pixel likelihood by modeling uncertain region around the foreground objects. The CNN used for defining the objective function and performing the inference is a mask track style CNN shown here, which we train using a two-stage scheme like previous work. Lucid data augmentation is also employed during the training of the CNN, where the training triples are generated using the given mask of the first frame of a video. We achieve state-of-the-art results on several challenging benchmarks. Finally, I will show some visual results of our algorithm here. Thanks for your attention and welcome to our poster at B4.
Hey, I'm Alexander Richard from University of Bonn, and I'm going to talk about action sets, or a very weakly supervised video segmentation without ordering constraints. So the actual idea is essentially, assume that we are given a kind of video as input, and isn't it moving on? I think there's something wrong. Just doesn't skip through the next slide. It should be 5 seconds, I don't know. Well, apparently it doesn't work. Let me anyway use the time to give at least a brief summarization despite of the technical problems. Just skip. Okay. I'm sorry for the technical issues. The essential idea is we are given the video, and we want to segment it into like different kinds of action segments in the temporal domain, meaning we only have essentially a video stream, and we want to find like from time A to B that there's a specific action, from time B to C there is another specific action, and so on. And in our work we assume that we only have a set of actions that occur in the video as only kind of supervision to train from, meaning we do not know anything during training about the time boundaries, and we also do not know anything in the training about ordering constraints within these videos. And yeah, so this is apparently a task that is pretty hard to work on and pretty hard to train, and we propose a model that can deal with this weakly supervised annotation and still get pretty good results that comes pretty close to models that use much less supervision. Due to the fact that the video apparently has some issues, I apologize for that. I suggest we just meet at the poster for any more details. Thank you, and apologies for the issues here.
Yeah, hello everyone. My name is Jianping Shi from SenseTime, and I'm here to introduce our work, low latency video semantic segmentation. Yeah, and video semantic segmentation has many important applications. For example, the autonomous driving needs to segment every frame in real time. And the challenges for video semantic segmentation mainly can be filled into two parts. First, it involves significantly larger volumes of data than image semantic segmentation. And second, in practical system, it should contains low latency. Yeah, for this problem, the previous method cannot achieve both good performance and low latency at the same time. Yeah. And to solve this problem, we have proposed a video semantic segmentation framework to overcome the limitation of previous work in two solutions. Actually, it includes two key components. First is how to select keyframes, and second is how to propagate keyframes across frames, keyframe features across frames. Yeah. Let's overview the system overview of our framework. And in the first frame, our framework forward the frame features into low-level features and high-level feature parts in our network to get the semantic label. And then next frame expands on a keyframe, depends on a keyframe selector. And if current frame is not selected as keyframe, we just propagate the high-level part of features from last keyframes. And otherwise, we forward the whole network to obtain the semantic features. And from this pipeline, and we can get efficient features from previous frames effectively. And the keyframe is selected by the derivation of semantic segmentation maps. And the derivation is, when the derivation is over some threshold, the frame is scheduled as keyframe, and the derivation is predicted by a small network. Yeah, and the current feature is obtained by, propagating the keyframe high-level feature using spatially variant kernels. Yeah, and the spatially variant kernels are also predicted by a network based on the low-level features shared as previous components. And from these spatially variant kernels, and we can better capture the adaptive features, from previous frames. Yeah, when a frame is decided as to be a keyframe, the feature is also, when the feature is, frame is decided as keyframe, the feature is also propagated from the last two frames as a fast track. And at the same time, a background process is launched to compute the high-level part of the network and then repeats the cached feature when computation is closed. And this is a slow track. The experimental results on Cityscape dataset shows that our method can achieve the competitive performance while maintaining low latency and compare with state-of-the-art method. And we also conduct experiments to show our adaptive scheduling method is better than fixed scheduler and threshold scheduler. Yeah, and that's all for our work. And thanks, and we'll come to our poster for more details. Thank you.
Good afternoon, everyone. My name is Huan Yu, came from Shanghai Jiao Tong University in China. Our topic is fine-grained video captioning for sports narrative, and our paper ID is 668. In this paper, we are interested in a new task, fine-grained video captioning. So what do we talk about when we talk about fine-grained video captioning? This illustration gives us a good explanation. Here is an NBA basketball game video. The first paragraph is the ordinary captioning, and the second paragraph is our fine-grained captioning. As you can see, the fine-grained one describes the scene more specifically. That is, it contains rich action details and interaction relationships. However, this task is not easy as it renders three main challenges. First one is the sports video always contain detailed motions. Second one is there are all kinds of complex mutual interactions in the game. And the third one is team sports usually have different subjects and relationships. And the main contribution of our work follows. First, we collect a new dataset named FSN dataset, and we will talk about it later. Second, we propose a novel metric. It is more proper for this fine-grained video captioning task since it pays more attention to the accuracy of the key motion and the description order. Third, we introduced a new network to solve this fine-grained narrative task. Here is the three subnetworks of our main model. In first part, we localize the spatial events, semantic entities, and discover the roles of the player, namely Team A or Team B. In second part, we introduce the enhanced human skeleton motion descriptor, since we observe that action details are highly correlated to players' posture, and the movement of the joints can be used to discern different actions. In third part, we use group relationship model to discover the interactions between players. And this is an illustration of our main model. As you can see, the first picture denotes the skeleton output, and we combine it with the optical flow to form the enhanced skeleton motion descriptor. Then we use MLP to reconstruct the features. In the lower part of this picture, we use one vector to represent the interactions of every region in the frame, and then merge them into one feature vector. Now we talk about our new dataset FSN. It contains 15,000 sports videos, and each video is annotated with timestamps, detailed descriptions, and segmentations. So this FSN dataset can be used for many tasks such as event detection, description, and segmentation. And we believe it can accelerate the emergence of other new tasks. Here is an example of FSN dataset. As you can see, each segmented player has its own label, and each description corresponds to the temporal proposals. And most importantly, this dataset will be published soon, and everyone can use these datasets. That's all. Thank you.
All right. Hello, everyone. I'm Li Jeff. I'm from Tsinghua University, and I'm going to present our work on end-to-end learning of motion representation for video understanding. This is a joint work with Wenbin Huang, Boqing Gong and Junzhou Huang from Tencent AI Lab, Chuanggan from MIT, and Stefano Erman from Stanford University. As you may already know, one of the most effective methods for video action classification is the two-stream neural network with a spatial stream and a temporal stream. And in this talk, I'm only going to focus on the temporal stream, which takes the optical flows as inputs to extract temporal cues from the videos. It is actually a two-stage pipeline. First, we need to compute optical flows using TVL1 algorithm, which is an optimization-based algorithm. And later, we should train a CNN based on that extracted optical flows. Clearly, it is very time and space consuming to first extract optical flows and then store them on the disks. So our basic idea here is to replace the original optical flow extractor with a neural network. We name it TVNet. So TVNet will have two features. First, it could compute optical flows. Second, it could be fine-tuned by backpropagation. Then with TVNet, we can enable the temporal stream to achieve end-to-end training and will not need to pre-compute optical flows and store them on the disk anymore. So now we'll show the details about our TVNet architecture design. First, let's recap the TVL1 method for optical flow estimation. It tries to minimize the function in the below, where the first two terms account for the smoothness condition, and the last term, rho U, corresponds to the brightness constancy assumption. And to extract optical flows, TVL1 resorts to an iterative process. We can find that every computation in the process is continuous and smooth almost everywhere. For clarity, we present each iteration in the TVL1 algorithm by a flowchart block, where the warping, gradient, and divergence computations are specifically defined. Now, we go further by unfolding the TVL1 block as a fixed-sized feed-forward neural network. If we replace the original computations by convolutional operations, we can further relax these convolutional kernels and the optical flow initializations to be trainable parameters to formulate a more expressive neural network. This will enable our network to learn more complex and task-specific features by end-to-end training. Then we'll show some experimental results. The execution speed for our TVNet is faster than most of the existing optical flow methods, including the FlowNet and the original TVL1 method, etc. We could further accelerate it by increasing the batch size and processing multiple samples in one forward pass. Moreover, the classification performance of our TVNet outperformed all compared methods shown here on both HMDB and UCF dataset. As our TVNet is initialized as a special TVL1, the initial structure is sufficient to produce promising results. So even if we freeze the TVNet parameters, it will still outperform most of the other compared methods shown here. And for more details, please check our website or come to our poster at B16. Thank you very much.
In this project, we present compressed video action recognition. Training video models is very expensive. Training on kinetic dataset can already take the whole week. And if you want to train on the full YouTube, it can take many years. So why is it so slow? What current models do is to treat a video as a sequence of frames and feed these frames into a CNN. While this was great, we argue that this is highly redundant, because the original video is only 1 gig in size, and we decompress them into 200 times bigger, with many frames being highly similar, and feed these redundant repetitions into a CNN. We think this is not ideal. So in this project, we propose to directly feed the compressed video into a CNN. Let's first see how video compression works. In the compressed video, we distinguish between iframes and p-frames. Iframes are stored as regular images, and p-frames use motion vectors to reference the previous frame. So what it does is to steal pixels from the previous frame. Anything that cannot be referenced are stored in the residual. So our goal is to train the CNN directly on the iframes, motion vectors, and the residuals. One naive approach is to process each of these frames independently. But unfortunately, this doesn't work, because each p-frame depends on the previous frame, and altogether it forms a long chain of dependency. To address this issue, we propose to break the dependency such that all the p-frames directly reference the iframe. This can be done by tracing back the motion vectors all the way back to the iframe and accumulate information along the path. And this can be done online efficiently without adding additional overhead. With this simplified dependency, this allows us to train a very simple model, but still respects the true dependency. We see that here, the output of pframe can directly reuse the information from iframe. In addition, since most of the information is in the iframe, we can focus our computation on processing the iframes and use only a very lightweight model to process the pframes. So overall, this is very efficient. Let's see how this works. We test our model on 3 action recognition datasets, UCF101, HMDB, and charades. In the first ablation study, we compared training on RGB images and training on compressed videos. And interestingly, we see that training on compressed videos leads to much better performance. If we look closer, we see that each additional thing helps, and using all of them leads to the best performance. If we compare it with other state-of-the-art methods, we see that our model achieved the best performance. If these models are combined with optical flow, all methods improve, but our methods still achieve the best performance. In terms of speed, our model is quite efficient. So in summary, videos are very redundant. So we propose to train directly on the compressed videos. And we show that it's not just faster, but also leads to a better accuracy. Our code is available online, and please come to our poster. Thank you.
Hello, my name is Ergus Ristani. I'm from Duke University, and I'm presenting features for multi-target, multi-camera tracking and re-identification. In MTMC tracking, the input is a set of video streams from different cameras, and the goal is to determine who is where at all times. The result is a set of multi-camera trajectories. In person re-ID, the input is a query image. The goal is to retrieve, using appearance similarity, those images in the gallery that match the query's identity. So these 2 problems will differ as follows. In tracking, we have to classify if 2 images come from the same identity. In re-ID, instead, we have to rank 2 images by which is the most similar to the query. So these 2 problems seem to require different loss functions. In this work, we address appearance learning for both problems simultaneously. If features are well separated, in the sense that the largest within class distance is smaller than the smallest between class distance, then both classification and ranking are guaranteed. For this purpose, we generalize the triplet loss into its weighted version. If weights are chosen meaningfully, we can learn a discriminative feature space for both problems. We propose to use weights from a softmax distribution. High weights are given adaptively to the most difficult examples in a batch, and all other examples receive their fair share of weights. Our weights address the imbalance of positives and negatives, are robust to outliers, emphasize hard examples, and therefore enforce class-well separation. In our evaluation, we will show that our adaptive weights perform better than the hard triplet loss with binary weights. Overall, the same model trained with our loss performs better than previous work. We also use our appearance features in the problem of MTMC tracking and compare our results on the Duke dataset. We put together a pipeline which extends our previous work. For each frame, we extract person detections using the open pose detector. In hierarchical order, we then compute tracklets, single camera trajectories, and multi-camera identities. We use the same reasoning in every level of the hierarchy. We extract appearance features using our train model, then compute identities using correlation clustering, and finally post-process trajectories to improve their quality. We conduct ablation experiments to understand the role of the detector and features. Better detections help little across cameras when features are weak. Good features are more useful than a good detector across cameras. and the best performance combines both good detections and good features. In this precision and recall plot, we show that our method outperforms previously published work. In these videos, we demonstrate few qualitative results. Green tails are for correct identification. The black tail is for the missed person in the group of 3 people. Blue and black tails will show identity switches. Thank you for listening, and see you at the poster session. We're also going to release code. Thanks.
Hi everyone, my name is Hui, and I'll be introducing you to a new action dataset called EVA, built by my previous colleagues at Google. So the goal of EVA is to promote Google research in human action recognition. Thus, we organize an EVA challenge in the ActivityNet workshop. Please come visit the workshop on Friday to get to know the latest results on EVA. So why do we want to still build a new action dataset? This is because we want to build a dataset to beat the following characteristics. And I'm going to explain them through the following EVA examples. Here is a collection of answer phone things from the EVA. As we can see, each atomic action is defined from 3-second segments, and each person performing the action is characterized by a bounding box in the middle frame of each action. As we can see, even though multiple people can exist in the scene, each action is corresponding to one bounding box. So some of the our EVA actions are object agnostic. So for this dig example, for example, people can dig with different tools, so the intra-class variation is very high. And here, we don't care about what object people send it to other, but really focus on the action by itself. So we have densely annotated 80 atomic actions in EVA, and each action corresponds to one of the 3 groups: pose, person objects, and person-person. And here's an illustration of our annotation framework. Each segment is 3 seconds, and they are densely sampled at 1 Hertz. So in order to annotate the labels, we first select movies from YouTube. We chose movies because they have realistic actions. And then we label all the person's bounding boxes and the actions in the middle frame of each segment. And we also linked enabling frames to construct the tracks. So now let's look at the statistics. EVA contains a total of 430 videos, and that gives rise to a total of 600K bounding boxes, more than 80K tracks, and 1.58 million labeled actions. Since we exhaustively label all the labels, our actions follow a long-tail distribution, ranging from a few dozens to hundreds of thousands. And here we can introduce some interesting coupling experiments. So here I show the top pairs of person performing from one action to the other. And here are the common co-occurrence actions that are performed by the person at the same time. So when we label this data set, we realize that this data set is extremely difficult for the current state of the art. So in order to prove this, we perform a baseline approach. Here is our baseline approach is a deviation from the fast RCNZ approach using RGB and flow as an input. We use I3D to encode the temporal information. Our baseline experiment has been shown on the 2 benchmark datasets, JMCDB and UCF10124. For both frame and video MAPs, our baseline approach significantly outperformed the state of the art for both benchmark datasets. However, the same model achieves only 15.6 on EVA, leaving a large room for improvement. Detailed analysis shows that EVA is particularly difficult for classification over localization, so there's a long way to go to accurate modeling of atomic actions. We have released our dataset since last summer, and we have been actively maintaining it. We are very grateful for all the contributors for giving us constructive feedbacks. Thank you, and please come to the workshop on Friday. Thank you.
I'm Hazel Doughty from the University of Bristol, and I'm here to present our work, Who's Better, Who's Best? Pairwise Deep Ranking for Skill Determination. We present the first attempt to assess skill from video applicable to a variety of different tasks, ranging from surgery to drawing and rolling pizza dough. As input, we use pairwise annotations of videos, indicating which video displays more skill, or that there is no skill preference. From these pairs, our method learns a function to output an overall skill ranking from any number of videos of the same or different individuals performing the same task. Now onto our method. Here's our input pair of videos, with one video showing a high level of skill. In order to gain an overall skill ranking for any number of videos, we divide each video into segments and use TSN to randomly sample a snippet from each segment. Each snippet is then fed into a shared weight Siamese network, either spatial or temporal. These networks output a score for each video in the pair from a consensus of the snippets. These scores are then fed into a margin loss function to evaluate the violation of the ranking of each pair of videos. Traditionally, two-stream CNN are used for short actions, where the full extent of the video needs to be considered. Since we're examining a skill which can be understood from all or any parts of the video sequence, we consider any uniform paired splits and evaluate each of the corresponding pairs in the loss function. To utilize more of the potential video pairings, we consider pairs of videos of a similar rank and propose a modified version of the margin loss function. This loss not only allows our model to utilize more pairs in training, but also encourages it to learn features which map pairs indistinguishable in terms of skill to similar scores. We present the new EPIC Skills 2018 dataset, which we use to evaluate our method. This dataset consists of 3 new tasks. Drawing, in which participants were asked to copy a reference image of a cartoon character or a grayscale photograph of a hand. Chopstick using, where participants are tasked with moving as many beans as possible from one tub to another using chopsticks. Dough rolling, manually segmented from the CMU MMAC pizza making activity, where participants have to open and roll out a can of pizza dough. And finally, we also evaluate on the surgical tasks from the existing Jigsaws dataset, where participants perform surgical training in knot tying, needle passing, or suturing. We annotate these tasks for skill using pairwise preferences obtained from Mechanical Turk. Workers were asked to watch pairs of videos simultaneously and select the video with the high level of skill. We take pairs where all 4 workers agree is consistent pairs to be used as ground truth, and obtain similar pairs from the overall ranking these annotated pairs form. By testing our method on each of the EPIC Skills tasks, we show our final proposed loss function outperforms the original margin loss consistently across each task on multiple modalities. We also note that temporal features are more useful than spatial for determining skill. However, most tasks benefit from the fusion of both modalities. We run ablation tests on the 2 streams contribution and the importance of the snippets. We visualize spatial attention across all tasks. In the dough rolling task, the network learns the importance of holes in the dough and stretched dough edges, whilst in the chopstick using task, we see that hand and beam position prove indicative of skill. Results on all tasks are available at our poster. Thanks for watching. Please come to poster C6 if you want to see more.
Hello everyone, my name is Theodos Ismailis and I'm here to present you the paper MXLSTM mixing trackless and visits to jointly forecast trajectories and head poses. The main idea of this paper is to use jointly people velocity and head pose for forecasting human trajectories. This idea was built upon sociological findings and data statistics. Usually, when head pose and oriented velocities are aligned, as shown, for example, here by the yellow arrows, this means that people do watch their steps. However, in many cases, this alignment stops. For example, notice the person here in the sequence below. Once he starts turning his head and then slows down until he stops for looking behind his shoulders. The idea here is that head pose might be really helpful for trajectory forecasting and especially at low velocities. These considerations have been confirmed by the data. In the graph here, you can see that the yellow curve represents the average angle omega between the head pose of the head pose direction and the average and the oriented velocity. And the white curve represents the average velocities at the Zara-2 dataset. As it can be seen, once the angle increases, the velocities are getting slower. Thus, in this work, we designed MXLSTM, which modifies the social LSTM by taking as input observed sequences of floor positions defined as tracklets. And at the same time, sequences of head poses, that is angles, observed either as ground truth or even estimated from a head pose estimator. MXLSTM predicts successfully the forecast trajectory successfully at giving results at the state of the art, but also V-sleds, which are that is meaning that predicting head pose behavior as a novel type of prediction. MXLSTM estimates numerically the covariance between oriented velocity and the head pose along time. So it captures instantaneous the relationship between these two, and at the same time, how do they change over the time? In the results, it is possible to see that when the average velocity slows down, the current state-of-the-art approaches, LTA, LSTM, and social LSTM, having higher mean distance error. This is because the trajectories are more irregular in these scenarios, and there are no any other cues taken into account. Contrary-wise, MXLSTM addresses these issues by taking into account the head pose cue. And as it can be seen, this is beneficial, and actually our work is the one that keeps consistent performance at low velocities. Some qualitative results of the previous curves can be seen here. In the first scenario, we have two people working together and occasionally speak to each other. In the second scenario, again, two people work together, but now they are talking to each other more intensely, causing them to slow down and at the end to stop. As we can see, in both cases, MXLSTM successfully models these behaviors, contrary-wise to the social LSTM that it fails. In the last case, we see that the person joins a group. And again, we notice that MXLSTM successfully models this behavior as well, while the social LSTM continues wrongly describes trajectories in irregular trajectories. Thank you for your attention, and see you at our poster C9.
Right, so given the technical difficulties, we've had the second spotlight, so we'll redo the spotlight again with Alexander.
Thanks for resolving the issue. Good thing is now you will all remember who I am. Okay, here we go, I think. Is it running? Great. Thank you so much. So, perfect timing, already the first slide. So the task is essentially we are given a video and we want to segment it into multiple segments. And for each of these segments, we of course need to find out what is the corresponding class label and what is the length of the segment. Given these two properties, we have a full segmentation of the video. The question is essentially how can we model this and how can we train this? Concerning modeling, we just want to optimize this posterior distribution of class labels and length given the video. Concerning training, we can go the easy way and assume we have full supervision, meaning for each segment we have the action class and we have the exact length. But this is somewhat unreasonable to assume because this requires thorough manual annotation and is really expensive if we work with a lot of videos. So let's remove some annotation. First of all, the length. So we only know the ordering of the actions, which is just like a sequence, golf, walking, driving, walking, this example, during training. So during training, we still would need to infer the actual length of each segment within the video, making the task already much harder. This is a bit more realistic, but not absolutely, because assume we have videos from YouTube where we only have like meta tags, then we would not know anything about the ordering. So what we propose here is a system where we are only given a set of actions and the corresponding video during training. So we have no temporal annotation at all, and we have no ordering constraints at all, making it particularly difficult to train it, because we have, compared to the previous case, a search space that is exponentially larger. So yeah, essentially to train this model, we would need to find the length and the orderings and everything during training already. How can we do this? Well, remember we had this posterior distribution that we actually want to model. In our work, we essentially propose to take this distribution and factorize it into 3 parts, a context model, a length model, and a visual model that are all trained separately with some heuristics. So they all will be weak, but jointly they will help us to get a pretty good performance. However, we are severely lacking data for this. Let me just give a very brief introduction to that. For example, for the visual model, we want to get for each frame of the video a distribution over the possible action classes, but we only know the action classes that overall occur in the video. So we apply a kind of multiple instance learning or multitask neural network to tackle this and get a very weak frame-wise action classifier. That alone would be really poor. However, we still have like 2 other components. One is the length model. Next question, how can we model length if we do not have any kind of temporal information? Actually, we can formulate a loss function that takes some heuristics into account. For example, short actions rather occur in shorter videos and long actions rather occur in long videos. So taking this into account, we actually can get a pretty good idea how long actions should be in practice. So we talked about the visual part, the length model. We still need some part that gives us information over action context, meaning over the ordering in which the actions occur in the video. Again, we have no training data for this. We have no ground truth information. So what we essentially do is we take the action set of a training video and sample an action. We already have our length model that is estimated, so we can also sample a length. And we can essentially do this for the complete video until we reach the complete video length. So we get a kind of sampled, ordered action sequence. And we can do this multiple times for all our training videos. We get a whole bunch of these sequences and train a stochastic grammar with this. So we have 3 models. Each of these is very weak, but if they are joined, then they are pretty good. So you can see here that we are worse than other approaches, but we have much less supervision, and we are pretty close. Thank you, and see me at the poster.
So that brings us to the end of an exciting session. Thank you. Let's thank all the speakers again.